Hi everyone, this is Ampacity and Conductor Sizing lecture. Things you'll need for this lecture: you need the 2017 National Electric Code book. If you don't have that, use the handouts that I gave you in class, which are Table 310-15B16 Ampacity tables, page 150 of the code book, Table 310-15B3A Pipe Fill Corrections, page 148, and Table 310.15b2a Temperature Correction, page 147 of the 2017 National Electric Code. In the United States, we use the American Wire Gauge, or the AWG scale, for gauging wires. The larger the number, the smaller the gauge. The smaller the number, the larger the gauge. From sizes 18 gauge up to 6, I can get those in either stranded or solid form. Once I get up to 6, it gets too difficult to work with. It's too stiff. So everything greater in size than a number 6 is going to be stranded, a collection of stranded conductors that make up the diameter or cross-sectional area of the conductor. Once I get past 1 gauge, I jump into a short category called the aughts. I can express that as aught, aught, or aught. Or simply I could say 1/0, 2/0, 3/0, 4/0 gauges. After I get past the aughts, everything jumps from a C-mil rating to a KC-mil rating, so much larger. And that's going to be on the lowest end, 250 KC-mil, and then greater than 1,000 KC-mil, huge diameters. In Article 310 of the code book, it lays out the identification and marking of conductors. So every 24 inches, I have to see stamped on the insulation jacket of the conductor these basic information. In the illustration on the top, I have a conductor that's a 10 gauge wire, 10 AWG. Then there's a set of 4 letters. That letter code relates to the composition of the insulation, applications I can run that conductor in, and the temperature rating of the insulation. So T relates to the makeup of the insulative jacket. HH relates to the temperature rating of that insulation. So 90 degrees C, that's the top rating. So we're going to see 3 temperature categories for conductors. They're going to be rated for 60 degrees C, 75 degrees C, or 90 degrees C. Most conductors that you use or will see are going to be rated for 90 degrees C. More on that later. And then the last letter in this sequence is N for the nylon jacket. So this particular conductor has a clear jacket over top of the insulation, which protects it from scuffing and damage. The illustration below that conductor is also a number 10 AWG, 10 gauge wire, and this letter coding is RHW, R for rubber, or the coating, the insulative coating on the conductor. H signifies that it's only rated for 75 degrees C, so this conductor can only take up to 75 degrees C heat. So when I pass current through a conductor, it gets hot as those electrons run through the conductor. So this conductor can carry only portion of a 90 degrees C conductor. It can't radiate enough heat out to keep the rated ampacity of that conductor is lower. And then the W, it signifies that it's okay or rated for wet locations. Table 310.15b16 is an ampacity table where I'm showing you just a portion of it, the portion that we're really going to be concerned with right now. So this ampacity table on page 150 of the code book, we're looking at the left-hand column right now. The left-hand column indicates the size or gauge of that wire in AWG, American Wire Gauge. Starts with 18 and goes, I'm only showing you down to 4/0, but it goes on and on and on to cover the KC mils in the sort. The next column over shows me the ampacity of a conductor if it only has a insulative jacket that's rated for 60 degrees C, the lowest rating. The third column is 75 degrees C, so it's medium range of ampacity. So this conductor can handle up to 75 degrees C. Temperatures, this is temperatures that are running through the electrons running through the conductor, generating heat, and this insulative jacket can only radiate so much heat out. And so in order to keep the insulation from melting off, I have to reduce the ampacity to keep it from overheating. And then next up, the highest category is 90 degrees C conductor, or insulative jacket on a conductor. And that has the ability to carry the highest amount of ampacity. So let's take a look at this. I'm looking at a number 12 conductor. Look at this first column, look at the number 12 conductor. And I slide my finger over to the right, to the 60 degree column, and that says that number 12 conductor, copper, can handle up to 20 amps, or the ampacity of that conductor is 20 amps. If I have a 75 degree insulative jacket on it, that same conductor, same cross-sectional area, same everything, but the insulative jacket can only handle now 25 amps. So as the insulative jacket increases its temperature abilities, so does the ampacity rating of the conductor. And then the last column, 90 degree column, that number 12 conductor can carry 10 more amps than the 60 degree conductor, and for a total of 30 amps, or the ampacity of that number 12 is 30 amps. So as the temperature rating of the insulative jacket goes up, so does the ampacity. The ability to not melt at those high temperatures and to dissipate heat is greater than the lower columns. Right, a couple words on this. When we go through our D rating of ampacity, so these ampacity ratings are for 86 degrees Fahrenheit and 3 current carrying conductors in a pipe. If I get more conductors in a pipe, I have to derate or downsize the ampacity of that conductor. If that conductor goes through a warmer condition than 86 degrees Fahrenheit ambient temperature, then I have to decrease the ampacity or the carrying capacity of this conductor based upon those conditions. When we go through the exercise, we're going to use a conductor with 90 degree insulation, but we're going to size the ampacity for the 75 degrees C column. And this is why we do that. Most or all the conductors that you have on a truck is going to be rated for 90 degrees C. After I derate the ampacity rating of that conductor for temperature, ambient temperature, and pipe fill, it generally lands within the range of that 75 degrees C ampacity column. In addition to that, all or most of the lugs that you see out in the field are going to be rated for 60 or 75 degrees C. If it's stamped as 75 degrees C, then I'm going to use the ampacity column of 75 degrees C. If it's not stamped for 75 degrees C, or there's no stamp on it at all, I have to assume that it's only rated for 60 degrees C, and I have to use the 60 degree ampacity column for my final ampacity of that conductor. So that's how it works. Just absorb this information, just let it roll. So I'm going to use a 90 degrees C, use that ampacity, derate it, but my final ampacity is going to be based upon the 75 degrees C column. Here I have the ampacity table, or my correction factors for temperature. So again, the ampacity table is based upon this 80 degrees Fahrenheit. And as I increase temperature or decrease temperature, the ampacity of the conductor changes, greater or smaller. So on table 310.15b2a, I have my correction factors. I'm going to use the right-hand column for my ambient air temperature, and it would be easily foreseeable to have temperatures of 140, 150, 160 in an attic space or on a rooftop. I'm going to correct that by running my finger down the Fahrenheit scale. Let's say I have 100 degrees Fahrenheit. Run my finger down to the right-hand column, to find 100 degrees Fahrenheit, which is between 96 and 104. Slide it to the left one column for the 90-degree insulation value. And my correction factor is 0.91. So I'm either going to multiply or divide by 0.91 to either derate a conductor or to increase the ampacity need by dividing. More on that in just a second. Then lastly, the last table I'm going to use is table 310.15b3a, which is on page 148. And as I increase the conductors in a pipe, the pipe fill, I have to decrease the ampacity. So if I have, say, 4 conductors in a pipe, I'm going to go to my chart. First column here says 4 to 6 conductors in a pipe, slide to the right. My correction factor is 80%. So I'm going to either multiply by 0.8 to decrease the ampacity of a conductor, or divide by 0.8 to increase the ampacity needs so I can size a conductor. Now, a few words about conductors in a pipe. 310.15b16 is the ampacity table is based upon 3 current carrying conductors in a pipe. If I have a 120 volt circuit, I have 2 conductors that carry current. I have a hot and a neutral. Current goes out on the hot, comes back on the neutral. 2 current carrying conductors. If I have a 240 volt circuit, single phase, I have 2 hots and a neutral. L1, L2, and then a neutral, a white neutral. So I have 3 current carrying conductors per circuit. If I have a series string, PV series string, coming off the array to the inverter, PV source circuit, one series string has 2 conductors, 2 current carrying conductors, one positive, one negative. If I have a 3-phase system, I could potentially have up to 4 current carrying conductors, 3 hots, L1, L2, and L3, or ABC, and then a neutral. So I have to count these conductors, how many conductors are going to carry current in my pipe. Here's an example. So I'm keeping the number of current carrying conductors in my pipe the same, is 3 for this exercise. But what I'm doing is I'm changing temperature. I go to the ampacity table on 310.15b16. I look for a number 12 copper THWN-2 conductor, which has an insulated jacket of 90 degrees C. It's the highest rated jacket. And the ampacity of that number 12 at 90 degrees C insulation is 30 amps at 86 degrees Fahrenheit, 3 current carrying conductors in a pipe. Now we're going to change temperature. So I'm going to decrease temperature to 50 degrees Fahrenheit. We're going to change the ampacity based upon that temperature. So I'm looking at 310.15b2a, which is on the right hand side here. I'm going to run my finger down the Fahrenheit column to 50 degrees. Oh, here it is right here, right on top. Slide my finger to the left to the 90 degrees C column. And my multiplier, or my correction factor, is 1.15. So I multiply 30 amps, my ampacity of a number 12 at 86 degrees Fahrenheit, 30 times 1.15, my correction factor, equals 34.5 amps. So I actually gain ampacity by running it in a cooler conditions, meaning like a cold storage facility, walk-in cooler facility, stuff like that where it's going to be cold. The exercise down below the next scenario is my conductor at 86 degrees Fahrenheit, still 3 current carrying conductors in a pipe. So 86 degrees Fahrenheit, run my finger down the column to 86 degrees Fahrenheit. Here it is, 78 to 86. Slide my finger over to the next column to the left, 90 degrees C, and my correction factor is 1. 30 times 1.0 equals 30 amps. No change. That's my rating ampacity of that conductor based upon my table 310.15b16 table. Now I'm going to increase the ambient temperature to 150 degrees, which is quite feasible to see in an attic or rooftop. It could be even much higher than that. I run my finger down the ambient temperature scale, Fahrenheit, looking for 150. Here it is, bingo, 150 to 158. Slide my finger to the left to 90 degrees C insulation column, and my correction factor is 0.58. 30 times 0.58 equals 17.4 amps. So I'm losing, oh gosh, 42% of my ampacity because I'm running in a hotter environment. The conductor can't radiate enough heat energy out of there to keep off that conductor to keep it cool. So I have to reduce the amount of electrons running through it, reduce the amount of current running through that conductor to keep it cooled down so I don't melt the jacket of the insulation. Next, I'm keeping temperature the same. Ambient temperature is fixed at 86 degrees Fahrenheit, but I'm increasing the number of current carrying conductors in the pipe. So I'm still using a number 12 copper. It's still ampacity rated at 30 amps. I still have a 90 degrees C insulation, and I'm fixed at 86 degrees Fahrenheit, ambient temperature. Right. So my first scenario, I have number 12, THWN-2, which is a 90-degree jacket. I have now not 3 conductors in a pipe, but 6 current-carrying conductors in a pipe. I'm going to go to table 310.15b3a, which is here on the right-hand side, and I'm going to run my finger down the first column, finding 6 conductors. And there it is, 4 to 6 conductors. Now I scoop my finger to the right, to the next column, and I find that my temperature or my pipe fill correction is 80% or 0.8. So I take 30, my ampacity of my conductor, times 0.8, and now my conductor can't carry 30 amps, but based upon pipe fill, can only carry 24 amps. So I have to reduce the current in that conductor because there's too many conductors in that pipe. More heat is being generated, it needs to be dissipated by the conductors. So the only way I can carry 30 amps on a conductor would be to upsize it. We're staying fixed at this 12 gauge, but in order to overcome this D rate, I would have to upsize my conductor in order to have more surface area, more cross-sectional area, more surface area to radiate this heat energy out and away from the conductor. Next scenario, I'm doubling once again the number of conductors in the pipe. I went from 6 to 12 now. Still in number 12, still a 90 degrees C insulation, still 86 degrees Fahrenheit ambient temperature. So I go to my table 310.15b3a chart table, looking for 12 conductors. Here it is right here, 10 to 20 conductors in a pipe. Slide over to the right-hand column. My correction factor is 50%, 0.5. So I take 30 times 0.5 equals 15 amps. So now, because I have more conductors in a pipe, I have to derate my ampacity of my number 12 by 50%. So this number 12 can't carry 30 amps. It can only carry up to 15 amps. And then lastly, I have 24 conductors. I go to my table, run my finger down to find 24. Here it is right here, 21 to 30. Slide over. My correction factor is 45%, or 0.45 is the decimal equivalent. 30 times 0.45 equals 13.5 amps. So I've lost, 55% of my carrying capacity of my conductor because I have 24 conductors in a pipe. So I have to be mindful of this as I increase the number of conductors in a pipe. Either I have to derate the conductor I thought I was going to use, or upsize to a larger conductor to get my 30 amps from point A to point B, or however many amps I need to get from point A to point B. All right, so now we're going to mix them all together. Here I have a number 10 conductor running through 105 degree temperature, 4 current carrying conductors in a pipe. In the first exercise, I'm going to derate the ampacity. In the second mathematical equations, I'm going to upsize the ampacity and determine what kind of conductor I need for that. All right, number 10 conductor, 90 degrees C insulation, running through 105 degrees ambient temperature for current carrying conductors. All right, that number 10 at 90 degrees C insulation can carry 40 amps. I go to my temperature correction table, run down the right-hand column to find 105 degrees. There it is right there, 105 to 113. Slide my finger over to the left to the 90 degree column and get 0.87. I go up here, multiply 40 times 0.87, and I derate the ampacity of my conductor to 34.8 amps. So I'm losing ampacity, or ability to carry electrons. Next, I'm going to do pipe fill. I have 4 current carrying conductors in a pipe, not 3. Go to my bottom table, 31015B3A, find 4 to 6 conductors in a pipe, slide over, and my correction factor is 80%. So I take my 34.8 amps times 0.8, and I get 27.84 amps. So I had to reduce the ampacity of this conductor because of temperature and pipe fill. And then the next exercise, I'm going to upsize my conductor, or determine what I need. So I need 40 amps to get from point A to point B. It's running through 105 degrees Fahrenheit ambient temperature. I have 4 current carrying conductors in a pipe. I'm still going to use a 90 degrees C conductor insulation. All right, here's my 40 amps. I go to my temperature correction table, find 105 degrees Fahrenheit. Here it is right here, 105 degrees Fahrenheit to 113 degrees Fahrenheit. Slide my finger over one column to 0.87 degree, 0.87. That's my correction factor. I take my 40 amps and divide it by 0.87, not multiply. I'm going to divide it, so I'm going to upsize that number. I do that operation and I get 45.9 amps. So I've upsized my needs based upon temperature. Now I go to conductors in a pipe. 4 conductors in a pipe. Go to my bottom table, table 31015B3A, find 4 conductors in a pipe, slide over to the right-hand column, 80%. So now I take my 45.9 amps, that's a typo, divide it by 0.8, and it equals 57.3 amps. So in order to get 40 amps from one place to the other, I need a conductor that can handle 57.3 amps, not 40 amps. So I have to go back to table 31015B16 and find a 75 degree conductor that can handle 57.3 amps. That's how you do it. Second example, I have a number 6 THHN copper 90 degrees C insulation. It's going through 90 degree ambient temperature, 90 degree Fahrenheit, and I have 9 current carrying conductors in a pipe. The first operation I'm going to do is to derate that conductor. Then I'm going to go through the same process, but increase the ampacity needs so I can identify a conductor that would carry that 75 amps from point A to point B. So I go to my temperature correction table, find 90 degrees Fahrenheit, and here it is right here, 87 to 95 degrees Fahrenheit. Slide my finger over to the 90 degree column, and my correction factor is 0.96. I take my 75 amps, divide it and multiply by 0.96, and I get 72 amps. So I derated by 4%. Next, I go to my conductors in a pipe. I have 9 current carrying conductors. Here it is, 7 to 9, slide across. My correction factor is 70%. So I take 72 amps, multiply it by 0.7, and that equals 50.4 amps. So I can't carry 75 amps in at number 6. I can only carry 50.4 for the given environmental conditions. 9 conductors in a pipe, 90 degrees Fahrenheit. Next operation, I'm going to find the conductor I need in order to carry that many amps, 75 amps, from point A to point B for these conditions. Here's my 75 amps. My temperature correction factor is 0.96. I divide 75 by 0.96, and that upsizes my needs to 78.1 amps. I take my 78.1 amps, divide that by my 70% for pipe fill, 9 conductors in a pipe. I divide by 0.7 and I get 111.6 amps. That's the size of conductor I would need to carry 75 amps through these environmental conditions of 90 degrees Fahrenheit, 9 conductors of current carrying conductors in a pipe. So I would go back to my table 31015B16, run my finger down the 75 degree column, and find a conductor that would handle 111.6 amps. All right, here's another example. I have two 20 amp circuits, 120 volts each, so I have 4 current carrying conductors, 2 hots, 2 neutrals. I have a rooftop temperature of 150 degrees Fahrenheit. I have 75 degrees C terminals that I'm going to terminate on. I'm going to use 90 degrees C insulation conductor. So the conductor I'm using is going to be copper, and it's going to have an insulative jacket of 90 degrees C. It can go up to 90 degrees C. All right, step 1. ID how many current carrying conductors and what are the conditions. I already did that for you. The conditions are 150 degrees Fahrenheit, 4 current carrying conductors in a pipe. Step 2. Go to table 31015B3A to determine pipe fill correction. So I do that. On the right hand side, I need 20 amps. Now I'm going to upsize my conductor based upon that number. So I go to my first column, 4 to 6, I have 4 conductors in a pipe. Here's my 4 to 6, run my finger across to the correction factor, 80%. So then I take my 20 divided by 0.8, which is the decimal equivalent of 80%, and I get an ampacity of 25 amps. So I would need a conductor that could carry 25 amps based upon this pipe fill. Step 3. Go to table 31015B2A for temperature corrections. I'm still running what I'm running through 150 degrees Fahrenheit conditions up on a rooftop. So now I have to bump that 25 amps up based on temperature now. So I go down my right-hand column of Fahrenheit, looking for 150 degrees Fahrenheit. Here it is right here, 150 to 158. Slide over one column to the left, and my 90 degree insulation, my correction factor is 0.58. So I'm going to take 25 amps, divide by 0.58, and I get 43.1 amps. So I can't use a 20 amp conductor to carry through these conditions from point A to point B. Based upon the environmental conditions of temperature and pipe fill, I need a conductor with the ampacity of 43.1 amps from point A to point B. Next, I'm going to table 31015. This is step 4, table 31015B16. Here's my ampacity tables, copper. Here's my temperature ratings on my insulations. Here's my gauges. Here's my ampacities right here. Let's zoom in on that. Because I have 75 degree terminals, all my corrections were based upon this 90 degrees C conductor, this insulation that can handle 90 degrees C or 194 degrees temperature Fahrenheit. But my terminals that I'm terminating on can only handle up to 75 degrees C. I can't use the ampacity ratings of the 90 degrees C. I have to reduce it and use the 75 degrees C column. That's just the way it is. Don't let it get you, don't be upset about it, just move on. I'm going to use the 75 degrees C column to find my final ampacity. So I run my finger down looking for 43.1 amps. Bingo, right here. So I need a conductor that can handle 50 amps or an